Okay, 8.1 exponential growth. Now, first thing we got to do is, we haven't talked about it, an exponential function. Okay, we've kind of been using them. It's anything where you have a number to the x power. Okay, exponential function kind of makes sense when you think about it, right? Okay, your base has to be a positive number other than 1. Okay, so b has to be greater than 1. Okay, for this to work. Nope, it has to be greater. Could be 1.1. Because if it's just 1, nothing's going to change. 1 to the 5th power is 1. 1 to the 2nd power is 1. Does that make sense? 1 to any power is just going to be itself. So it has to be greater than 1. Otherwise, there would be no point in having an exponential function. Okay? When you graph these, okay, I'm not going to go through a lot of graphs with you. When you graph it, make an XY chart, plug it in, just like you did yesterday on your test. Okay? Did that not work out well, or why? Okay? So, if you had to graph, okay, maybe I give you y equals 4 to the x. Okay? You pick your xy, and you plug in -2, -1, 0, 1, and 2. Now, you will run into times here where you have to alter these numbers. Okay? You might have to alter those numbers to get more things on the graph or a better looking graph. Okay, that's okay. If you have to alter those, it's not a problem. Okay? Just be aware that you might have to do that. Okay? Now, your exponential, specifically growth functions, are typically going to look like this. Okay? They're going to grow. They're going to get bigger. Okay? As your x gets bigger, your y is going to get bigger. Okay? Because we're growing, right? Okay? So if I plug in a bigger x, my answer is going to get larger. Okay? That's typically what your exponential growth functions are going to look like. Okay? But any exponential function is going to have a curve that looks something like this. Okay? Maybe it's over here. Okay? That would be an exponential function just based on what it looks like. Okay? So that's just the general form that they're going to look like. Again, we're not going to do a bunch of graphing here because you should be able to plug in numbers and get a graph, right? Can we handle that? Okay? If not, when we get to our homework, let me know, and I can help you. Okay? We are going to do one here. I don't know if I have a graph. I don't know why this page got put there. One second, let me get a graph put up here. Apparently I don't have them saved on your guys' files. Maybe. I can't find the one I usually use. Alright, here we go. We'll just use this one. Okay, so I have my graph. It tells me that I want to use the function y equals 1/2 3 to the x. Is that an exponential function? Yeah, because I have my variable as an exponent. Okay, so I'm going to make my xy chart, and I'm going to plug in. Okay, when I plug in -2 here, okay, so 3 to the -2 is actually what? It's actually 1/9. What's 1/2 times 1/9? 1/18. Okay, 3 to the -1 is 1/3 times 1/2, 1/6. 3 to the 0, 1 times 1/2, 1/2. 3 to the 1st, 3 to the 1st, 3 times 1/2, 3/2. 3 to the 2nd, 9 times 1/2, 9/2. And you can think about those as decimals if you need to. Okay, so let's go ahead and graph those. So I have -2, 1/18. I have -1, 1/9. I have 0, 1/2. I have 1, 3/2. And I have 2, 9/2. So 2, 4, 6, 8, 9. Okay. So then I have my graph of my exponential function. Is that a growth function? Is it getting bigger? Yeah, it is. Okay, now we're going to have some rules here for a growth function in a second. A couple other things. Okay, and I passed it earlier, okay, but we're going to talk about it now. What point or what number can I get super close to but never actually touch? Well, I passed 1, right? I went from 1/2 to 3/2, so I hit 1, 0. Because if I plugged in -3, I'm just going to get another smaller fraction, right? And another smaller fraction, and another smaller fraction. Okay, I can plug in -30, and I'm still going to get a fraction. So I'm never actually reaching 0, am I? Okay, so this line is what we call our asymptote. Asymptote. Your asymptote is a line which you come infinitely close to but never actually reach. Okay. In this case, there's not a vertical asymptote because I could keep picking x's, right? Yeah. And it'll keep giving me y's. Okay. I do have a horizontal asymptote because I'm not picking my y's. I'm picking my x's. So I could come clear over here. Am I ever actually going to reach that 0 mark? No. Okay, so that would be your asymptote is at 0. It's not always going to be 0. Okay, so don't think that it's always 0. Okay, there will be times where maybe your graph is moved up here. Okay, your asymptote can be different things. In that case, your asymptote's probably 2. Or the line, it'd actually be y equals 2, right? That'd be the line y equals 2. In this case, you could just say the x-axis. Okay. So just be aware of that. An asymptote is a line that you come infinitely close to, but you never actually touch. Okay. Now, this was exponential growth. To be exponential growth, yeah, you could graph it and figure it out, or you can just look at some numbers. Okay. In the equation y equals ab to the x, okay, so we're adding another number out in front of my b to the x. A is greater than 0, and we already know what about b. It's bigger than 1. Okay, so to make that an exponential growth function, basically your a has to be what? It's got to be positive, right? Yeah. So what do you suppose it would be called if it was negative? It'd be decreasing, right? So we'll talk about that later. It's actually going to be called exponential decay. Okay, growth and decay. So we're going to be working with growth and decay functions. With us, Devin? Okay. Okay, this next part, there's a couple things here that you might want to get on your note card. Do you need a new note card? You should have yours still. Do you need another one? Huh? I told you what? Yeah, for your graphing. If you need another note card, you can come get one. Sure thing. All right. Growth factor. Okay. This is just going to be an equation for you guys. It's going to be y equals. Make sure I get this right. A 1 plus r to the t. Okay. Basically what this is, there's a lot of things that we can use this for. A lot of exponential growth is used in like banking scenarios. Like how much money am I going to have after this amount of time? What's a house going to be worth after this amount of time? That would actually be a decay model. Okay? Or inflation, stuff like that. Okay, so your T is your years. Okay, it's time in years, so T equals time in years. Okay. A is your initial amount. And R is your rate, or your percent increase. So looking at example 3, it tells us that in January 1993, there were about 1,313,000 internet hosts. During the next 5 years, the number of hosts increased by about 100% per year. Okay. We want to write a model giving the number h in millions of hosts t years after 1993. And then know about how many hosts there were in 1996. Okay. So looking at that, okay, it's the same function, except now instead of y, we have h. Okay, because we're we're giving the model for the number of hosts. Okay, so that's what we're trying to find. Okay, you still have your a, you still have your 1 plus r, and you still have your t. Okay. But when we set this up to solve, what is a? It's my initial amount, right? Which was how many hosts? 1,313,000. Right? Does this 1 ever change? No. Okay. My R is my percent increase. What percent do I increase by? 100. Now, that's a percent, right? When I'm actually using a percent, I use the decimal version, which would be, in this case, it would be 1. Okay? And it tells me that we want to know how many hosts there were in 1996. So what's my time in years going to be? 3. Because that from 1993, that's 3 years away. Okay, so you actually have 1,313,000 times 1 plus 1 is to the third is. So what is that? 0, 0, 0, 4, carry your 2. Did I do that right? Or did I mess up somewhere? Oh, yep, it is. You're right. Okay. What would my label be on that? Host, internet host, yep.
How'd you get that time?
The 3? Because it told me that I wanted to know how many hosts there were in 1996. It told us how many there were in 1993. So the difference between 1996 and 1993 is 3 years. Does that make sense?
Yeah, I was looking a lot more online.
Okay. Okay, so there are other ways you can use the exponential growth. The main way is on this next page. Okay, so flip over. This will be the last example we work on here. This is about compound interest. This is the one that's going to be most relevant to you guys. I would. I'd put the equation on your note card. Some of you might have used this already with Mrs. Dorrit. Yep. Okay. So your compound interest is interest paid on your initial investment or your principal. Okay? And on previously earned interest. Okay, so your equation is A equals P, which is going to be your principal, times 1 plus R over N to the NT. Okay, and we'll go over all these labels here in a second. What's A stand for, probably? Yeah, it's your amount. P is your initial principal. What's initial mean? Yeah, you're starting. Okay, what you started with. R is your annual rate. Now you again have to remember when you plug that in, do you plug in it as a percent or as a decimal? As a decimal. Okay, and then N is the number of times compounded annually or per year. Oh yeah, sorry, T is time. In years, yep. Yep, T is always going to be time in years. Okay, so we obviously have a lot more variables here to work with. Okay, so the example they give us. Okay, you deposit $1,000 in an account that pays 8% annual interest. Find the balance after 1 year if the interest is compounded with the given frequency. They give us annually, quarterly, daily. Okay, so we know, let's just think about some of our numbers here. What's my P? It's my initial, what is it though? $1,000, right? Okay, so I started with $1,000. My R is my rate, 8% or 0.08, which is the number we're going to plug in. Okay, and I want to find the balance after 1 year, so my T is 1. Okay, and then the N is going to change, right? Because that's the number of times compounded. How many times is it compounded if it's just compounded annually? Once. So when I plug this in, okay, I have A equals 1,000 times 1 plus 0.08 divided by, in this case, 1 to the 1 times 1, right? It's NT, correct? Okay. Probably going to need a calculator for this one, right? Shouldn't. Okay. So 0.8 divided by 1 is 0.8. 1 plus 0.8 is 1.08 to the first $1,080. Okay, that's in a year. So you made how much? You made $80. That's a really good return on an account. Actually, 8%, that's a lot. Okay, if you can ever find something that's returning your money at 8%, you want to take it.
How likely is that?
Now, very unlikely. If you find it, you better talk to me about it because I want to invest all of my money in it. Okay? So what if I went back and I changed it? They want to change the next one. They want to do quarterly. What does that mean? So that means they do it 4 times a year, right? Because how many quarters are in a year? 4. So what numbers change? The bottom one changes to a 4. And it's going to be 4 times 1 now, right? Okay. What is 0.08 divided by 4? To the 4th power, though. So I actually have 1.02 to the 4th, which is, what is that? .08. And for how much cents? Okay. So which one's better, annually or quarterly? Obviously, right? You're getting your interest 4 times a year as opposed to once a year, right? Hey, what about when it says daily? That's going to be pretty sweet. So that 4 actually changes to a 365. So up here I have 365. What do I get? Yeah. And 28 cents? Now, obviously that doesn't seem like a big difference, right? But the more times it happens, the more years you're in it for, the more that number increases, right? Okay? Again, if you ever find anything with 8% return like that, you want to take it. Okay, you're probably not going to find that anytime soon. If you do, let me know, because I want in. Okay? We get out of here at 20? Okay. Let me look and see what we got here for an assignment. Basically, it's just plugging stuff in for the most part, guys. Got all evens for you.